Hey, what's up everybody? It's Matt from EGR246. Here's my co-op demonstration problem. It's going to be co-op problem number 1 from chapter 7. And basically we have this beam is constructed from 3 boards. Here's board number 1, number 2, number 3. And here's all the steps that we're going to go over through the centroid. And ultimately we want to find the shear force V that the board can sustain, and based on the condition that the allowable shear stress is 250 psi. And then after that we want to find out how far each nail should be spaced. If each nail can resist a shear force, just call it V resist, is 500 pounds. So the first thing we need to do is find the centroid of our beam here. And looking at it, we know it's going to be right around there somewhere. So I actually used ME Pro to calculate the centroid already. Whoops. And ME Pro, my TI-89, told me that it was 8.625 inches from the bottom. Afterwards, I looked for the centroidal moment of inertia, which I also used ME Pro to figure out, or to calculate. And that was 1.1964 times 10 to the third inches to the fourth. Afterwards, we wanted to find Q at the centroid, and that'll be the maximum Q value. That's equal to the sum of the Y bars times A, or times the area of each member. So basically, we have our centroid right here, and we're going to take the distance from the neutral axis to the centroid of this member and the centroid of this member, multiply those by the areas of each corresponding part, and that'll give us our Q value. So for part number 1, it'll be 10 inches times 1.5 inches times 4.875 plus 0.75, and this value is just Y bar, and it's just the distance from our centroid to the centroid of the top beam, the top member. I probably should have shown you guys how I calculated that, but I've written down in my notes, so I'm sorry about that. But basically, if our total beam is 15 inches tall, and we know that the centroid is 8 and change or 8.6 from the bottom, that means it's 6.3 and change from here to the top. And it's basically 6.375 minus 0.75, which is the same as this guy. And then we also want to add the Q value from our centroid to this part, and the area of that will be 4.875 divided by 2, which is basically the distance from our neutral axis to the bottom of our flange, and divided by 2 will just give us this point right here. Times our area, which is 4.875 times 1 inch. Summing those together, we get Q max is equal to 96.25 inches cubed. Now we want to use the relationship of shear stress. Tau equals VQ divided by the moment of inertia times the thickness. And we're going to solve for this guy right here. And we were given that the allowable shear stress is 250 psi. We calculated the moment of inertia to be 1.1964 times 10 to the third inches to the fourth. And the thickness of our web here is 1 inch. So, and in the top, that'll give us the units of inches to the fifth, and this is pounds per square inch. So we're left with inches cubed. We divide it by our Q, which we calculated to be 96.25 inches cubed, and all the inches will cancel out, and we're left with just pounds. I calculated this to be 3.11 kips. Now we want to compute Q for both the top and bottom flanges. And we know that Q at the top is y bar times area. So we're going from the centroid to the centroid of this top flange. Well, we already did that, so that's pretty simple.